Alright, now we're going to talk about the second method for finding delta H, the change in enthalpy. And this is using a calorimeter. And a calorimeter, this would be the lab process. So a couple quick terms: calorimetry is the measurement of heat transfer, and a calorimeter is a device that we use to measure that heat transfer. So remember, heat is not the same thing as temperature, and we cannot measure the flow of heat directly. So we can't just stick a little device in there and measure how much heat is being transferred. But we can measure the temperature, and we can correlate the temperature with the transfer of heat. Heat is a measurement of joules, temperature is a measurement of degrees. So we find the degree change, we find the heat flow. So one of the things about temperature is that things don't heat up or cool down at the same rate. Where that comes into play is specific heat capacity. We symbolize that with a lowercase c. So heat capacity is the amount of heat or amount of energy that's required to raise the temperature of 1 gram of substance by 1 Kelvin. So water, for example, it would take 4.184 joules of energy to heat 1 gram of water up 1 Kelvin. Iron, on the other hand, only requires 0.45 joules to raise it 1 Kelvin. So that means then that if you apply heat or apply energy to both of these at the same rate, so you put the same amount of joules in both of them, the iron will get hotter faster than the water. And this makes sense. If you think of a hot summer day, if you go out and your car's been sitting in the sun and you put your hand on something metal on your car, it's going to burn. Whereas if you go and you touch grass, which is largely water, it's not as hot. Even though they've been sitting in the sun for the same amount of time, iron will get hot faster than the grass would. And that's just heat capacity. So it takes more energy to heat up water than it does iron or metal. But we can use that information then in this equation right here. So let's say the iron went up by a certain amount of temperature. So it went up by 10 Kelvin. Knowing its specific heat capacity, that number right there, and then the mass of the iron, we can calculate how many joules of energy it took to change that temperature. And notice we have units on there. Those units can then be used in stoichiometry, and so this is really a conversion factor. It takes 4.184 joules to raise 1 gram, 1 Kelvin. It takes 0.45 joules to raise 1 gram, 1 Kelvin. So then if we had 2 grams of iron, how many joules would it take to raise 1 Kelvin? It would take 0.9. If we had 3, we would multiply it by 3. And so we can use that then in some conversion factors as well. Although a couple tricks with this number: notice how a lot of times specific heat capacity is in Kelvin, but when we measure temperature, a lot of times we're going to be using Celsius. So you've got to make sure that you have units that match when you use this. And so here's what coffee cup calorimeter would look like. And this is a nice, cheap, easy lab experiment that we can do. So what this uses is a coffee cup that's sealed off with usually a piece of cardboard, and you stick 2 holes in it. One is for a thermometer and one's for a stir stick. And then you do a reaction inside the coffee cup. So usually it's a reaction that involves solutions. So you mix 2 solutions together, and then you measure the change in temperature as those 2 solutions react. And for this, outside here, this would be the surroundings. So this would be the universe. And inside here, this would be the system. And so the goal of a coffee cup calorimeter is to insulate the system from the surroundings. You want to measure the change in temperature, but you don't want the surroundings affecting that change in temperature. If this is an exothermic reaction, you don't want the heat or the energy that's being given off to go to the surroundings. You want it to stay inside of the system. If it is taking energy in, you want it to take energy from the system, not the surroundings. We can't really measure the surroundings. If there's a change in temperature, so if it's exothermic and it's giving off energy and it's giving it to the surroundings, we can't stick a thermometer outside and measure the change in temperature of the room. It's way too big. So this is just a means of isolating our system so we can focus just on it and its changes and interactions. So for this, we use the delta Q equation. So delta Q is the change in heat lost or gained by a particular reaction. So let's say, for example, we do this reaction with 2 grams, and we find out that 2 grams, the delta Q was, we'll say, 400 joules. We can't say, hey, every time we do this reaction, it's going to let go 400 joules of energy. No, for 2 grams, it released 400 joules. If we went up to 6 grams or 1,000 grams, it would not be the same amount of joules. And so that's why delta Q is different than delta H. Even though they both measure joules, they both measure energy, Q is the heat lost or gained by this particular reaction. Delta H is the amount of energy released per mole. And in coffee cup calorimetry, this would just be the mass of the solution rather than the mass of like the iron or anything like that. Specific heat, we usually use water because if you think about solutions, they're mostly water, and so that's going to be largely just what our specific heat is. And with these, we're just mixing two solutions together and then measuring the change in temperature. And then we can correlate that to delta Q. So you mix the two together inside the coffee cup, you measure the change in temperature, and use that then to calculate the Q of the solution. So let's say, for example, we calculate it to be positive 568. So that's a positive number, which means that the solution itself gained energy. And if it gained energy, where did it get that energy from? It got it from the reaction. So if the solution gained 568, that means the reaction lost 568. That means it is an exothermic reaction. A way that we can always remember this is that the negative of the delta Q of the solution is always equal to the delta Q of the reaction. It's always opposite. So if the solution gains 568, that means the reaction lost 568. If this was a negative 568 gained by the solution, that would mean that the solution lost energy, and that energy was picked up by the reaction. Alright, so we'll do a practice problem together. In this one, we're dropping a piece of iron into some water, and we're measuring how the temperature of the water changes. We're going to answer 3 questions. So how much heat was gained by the water, how much heat was lost by the iron bar, and then what was the specific heat of iron. Alright, so let's do that first question, how much heat was gained by the water. Remember that the equation is delta Q equals mc delta T, and so we're going to calculate this using the mass of the water, specific heat of water, and then its change in temperature. And so here it is with all the numbers plugged in. We had 350 grams of water. Since it is water, we can use water's specific heat, and the change in temperature started out at 25 degrees Celsius and changed to 28.4. So there's our final temperature minus our initial temperature. And you notice that I'm using degrees Celsius this time. Works out all right because the conversion is just adding and you subtract it away anyway. So if you use Kelvin degrees Celsius for this particular equation, it doesn't really matter. But then if we want to go through, we can see that grams cancels out grams. Degrees Celsius will cancel out our degrees Celsius. So we'll be left with joules, which is great. Always check your units to make sure they cancel out correctly. Joules matches up then with delta Q, so we know we're good to solve here. And so if we go ahead and plug these numbers in, we would find out that the delta Q for the water is a positive 4979 joules. So that means that the water gained 4,979 joules worth of energy. So if water gained 479 joules of heat, how much was lost by the iron bar? Remember, this is an isolated system because it's in that coffee cup, so this energy that was gained by the water was lost by the iron. That means that delta Q for the iron would be a negative 4979 joules. So that means this was an exothermic process. It was a loss of heat by the reaction, or by the iron. Alright, let's find the specific heat of iron then. How much energy does it take to raise it by 1 degree Celsius? Remembering that the change in energy is going to be mc delta T. And in this case, we are looking for C. So I'm going to go ahead and rearrange this equation before I plug numbers in. So that means the heat capacity is going to be equal to the delta Q divided by mass times delta T. So delta Q we already found, and we found it to be negative 4979 joules. We know that the mass of the iron was 97 grams. And then for the delta T, we know what the starting temperature was for the iron. It was 143 degrees Celsius, but it never tells us what the final temperature of the iron was. It tells us what the water was, but not the iron. How can we figure that out? Let's see. Yeah, they would be exactly the same. So remember, when we put two things together, they transfer energy until they get to that state of equilibrium, which means at that point their temperature will be identical. So if we know the temperature of the water, we know the final temperature of the iron. Think about it, if the iron was still hotter than the water, then it would keep transferring energy to the water to warm it up. If the water was hotter than the iron, it would transfer energy back to the iron to warm it up. So at the end, they're going to have the same temperature. This is a great illustration of heat capacity too. Remember the water? The water gained 4979 joules, so it gained the same amount of energy as iron lost, but water only went up by about 3.5 degrees. Whereas look at this, the iron changed by about 120 degrees. So a huge temperature shift by iron and a small temperature shift by water. It's because water's got a high heat capacity, iron has a very, very low heat capacity, so it takes less energy to change the temperature of iron than it does the water. And if we look at our equations here, none of the units will cancel, which is actually good because then when we calculate this out, we would find that the delta C is 0.45, and we're left with joules on top, grams on bottom, and degrees Celsius on bottom as well. So joules over grams degrees Celsius. Those are the units of heat capacity, so this worked out perfectly. And if you work this out on your own, what you would find is you have a negative delta T right there and a negative right there, which means we wind up with a positive C value. So what we find from this then is that 1 gram of iron would require 0.5 joules of energy to raise it 1 degree Celsius. So to wrap this up, let's talk about the difference between delta Q and delta H. So delta Q for a particular reaction is the heat lost or gained in the experiment, so that experiment, whereas delta H is the heat lost or gained in a balanced chemical equation. So delta Q is very specific to a particular reaction then, whereas delta H is more general. It applies to an equation. This one is a lot more useful, which is why we talk about enthalpy more than we do delta Q. Enthalpy is you can use it in any different situation. So for example, let's look at the combustion of methane. Let's say we conducted an experiment where we burned 2 grams of methane. When we did that experiment, what we would find then is the delta Q of that particular reaction. So that number is useful to us only in that particular reaction, because when we burn 2 grams, we get that much energy. Great, but what happens if you burn more than that many grams? Well, that's where the delta H comes in more handy. So then the delta H for this reaction down here would apply for 1 mole of methane. So if we knew what the delta H was for 1 mole, we could figure it out for 2 moles, 3 moles, 4 moles, etc., etc. And making the conversion from this number to that number is easy and something you'll have to do pretty often. We would just say, okay, if 2 grams released this much energy, then we can convert 2 grams into 1 mole and say, all right, then 1 mole would have released this much energy. And that would be the number we can use then for this reaction.